So we had, as I mentioned, the only two that would be specific are hydrochloric acid, which is given the name, what's its chemical formula? HCl. Okay, and technically speaking, that's when it's in its aqueous form. So they a lot of times will have a little AQ next to it. Versus if it's a gas, you usually say hydrochloride, which is what you get from the table. And the other one's hydrobromic acid. Those are the only two. Because even something like acetic acid, I would give you the formula for it, which is vinegar's diluted acetic acid. That's one that you come across in nursing. And there are others that you come across in nursing, but I would give you the names. Hydrochloric acid is the old name for it. Sometimes it's muriatic acid. If you have like a swimming pool, or sometimes some of the cleaners may say it's muriatic. This is hydrochloric acid. I can't remember the common name for the hydrobromic acid. Okay, but as a review, in general, remember the bonding, the two broad classes of bonding. There was covalent, which we'll get to in more detail later on this semester, and there's ionic, which this is what most of Chapter 5 really has to deal with, is ionic. And what's the difference? What is ionic? What do the elements that are coming together to form a bond, what's so special about them? They do not share electrons. So in the sense that one of the elements has become an ion by taking the electrons from another of the elements, it's become an ion. And so, these do not share electrons in their bond. So one literally takes it from the other. And so an example, of course, is sodium chloride. That's the one that I always remember, NaCl. And whereas covalent would, what do? They share electrons. Now there are some exceptions, but typically speaking, like if you just had to guess, like the Miss America World Peace kind of answer for this, ionic bonding is going to usually occur between a metal and a non-metal. Okay. So that's most often between a metal. So that's why it's really important to know which ones are metals and non-metals based off of their location on the periodic table. Whereas usually covalent bonding is between what? Between nonmetals. Whoops, that is not how you spell nonmetals. That is non-mental. Non-metal. And so a textbook example of that, which also kind of helps with knowing how to name things, is I just think of CO2 or CO. CO2 is carbon dioxide, CO would be carbon monoxide. So they're the ones that will have the mon, di, tri, etc. Okay, and then we also had an example. There are ones called polyatomic ions. These can be polyatomic, they don't have to be. And just an example of that. And once again, I would give you the table. I'm going to put my negative charge in a circle, that way you can tell it easier from the letters and everything. That's nitrate, NO3 minus. And that's where the N and the 3 oxygens behave as one unit in forming an ion. Okay. That's why it's called polyatomic. It's more than one atom coming together to form the ion. But they all behave as one group. Okay. So one other thing, trying to determine the charge of the ions and writing out the formulas, the chemical formulas. Let's just do some examples. Let's say, for example, that we've got, towards the end there, there are certain, like the transition metals, there are times that they can have more than one, they can form more than one ion. So chromium, for example, can form at least chromium 2 and chromium 3. So remember, the transition metals are the ones that are kind of sunk in on the periodic table. So if we had a chromium and we had nitrate, since I just used nitrate as an example, once again, a lot of times I try to put circles around them so that way, I mean, it's easy whenever it's got more than one. Oh, it's just a plus or minus, sometimes it's kind of hard to tell with my writing. And so we were now wanting to form and write out what the formula is when these two form an ionic bond with each other. It's pretty simple. What you do is you have Cr, and we know that it's NO3. And all you do is you move the charge of one down to be the subscript of the other. So the nitrate's a -1, so it means you're going to have one chromium, and it's going to take 3 nitrates, because each. So if I rewrite this now, it's going to look like this. Remember, we actually don't write the 1 in, but for the nitrate, you have to put parentheses around it. And then you put the 3. So it behaves as 1. If I were going to name this one literally would be named chromium 3 nitrate. Once again, you'll have a periodic table, have access to the periodic table to know how to name that one. Okay, that's why if we looked at another example, sodium is at +1 charge, bromide, well, will become bromide. Bromine, when it's an ion, is a -1 charge. So I'll give you a moment to write out what the chemical formula would be for it. And actually, I'll write another one out in a different color too. That way you can do more than one. So if we have potassium and oxygen. So that way you can give a moment to do a couple. Once again, these are all ionic. It's between 2 different ions. And as a review from the last class, remember we always put the non-metal first, followed by the metal. Okay, so this first one, we just rewrite N, A, and B, R. Would they have subscripts on them? No, because the plus will go here. I mean, the 1 would go here and 1 would go there, and so they're both 1-to-1 ratio. So it's just NaBr. What about K and O? So we know it's going to have a K and an O. Are there going to be any subscripts on these? K2, because see, since the oxygen's a 2 negative, that means there's got to be a 2 here. And the reason why is you need the charge overall to balance out. That's why there is a mathematical formula. Here, I'm going to rewrite it so that way it's easier to see. The mathematical formula literally means you've got to take, there's 2 of each +1 charge in the potassium plus the -2 charge of the oxygen. It's got to equal 0. And so that's where it comes from. But the easy way is just to remember that they've got to the charge becomes a subscript on its fellow partner. Now, what happens though is if we have something like calcium, which is a 2+, that's supposed to be an A, and we've got sulfur, which is a 2-. Now, It's still true. You can still write it as Ca2S2, but that's not the final answer. And the reason why is both of these are divisible by 2 for an ionic bond. You can't do that with a covalent bond, but you do with an ionic bond. And so it becomes CaS. Okay, so if they have a common denominator, then they're going to cancel out.
That would be the empirical formula.
That's both the empirical and the ionic formula.
Okay.
Okay, so let's work the other way around. I'm going to give you the formula, and then we can name it. And once again, you'd have the table, so if you had it printed out or something. And I'm going to start with one that would probably be one of the most difficult, okay? Cobalt 3 Sulfide. And then I'll do another one, isn't it? And let's say that we have one that's calcium sulfate. Everybody, a moment to get. Once again, you would always ask yourself, is this going, is it a covalent or an ionic bond? Both of these are ionic. Because they're going to be either between a metal and a non-metal, or they could have these polyatomic ions, which that's sulfate is an example of that. So when they do one with the polyatomic. Okay. So, once again, you would have the table and the periodic table and the other table for sulfate. So, cobalt, which is chemical formula CO. So on the periodic table, you would look up cobalt or on the table. Now, cobalt is a transition metal. It can have more than one charge. So what's the charge on this cobalt? So with transition metals, for the sake of this class, you would always need to know what the charge is. There are a couple that only have one, but I'm not going to have you memorize the exceptions to that. So what's the charge on this cobalt? 3, because they always put it in Roman numerals. I don't know, they just always put it in Roman numerals. So we know that's going to be a 3 plus, because it's a metal. Sulfide, what element makes sulfide? Sulfur. All that IDE means is that it's negatively charged, okay, or that it's the non-metal that's involved in the bonding. Okay, once again, that is on the table really, but it's sulfur, and you would have to look to see what the charge is on the sulfur. The charge is a 2 minus. It'll be on the table, but there's also a way to tell on the periodic table. It's like if you didn't have, I'm going to use the table, but if you didn't, the way to tell. Remember that noble gases are neutral. They're perfectly happy. So you just count over how many from the right. Count left, and I'll tell you. So these like to be -1. These like to be -2. So it's like this way it goes the opposite direction. This is +1. These are +2. Okay, so it's a 2 minus. So that's the hardest part, is just going through the names to try to figure out what the charges are. And now we just go ahead and we write what the chemical formula is. So what's the chemical formula for this one going to be? We know it's going to be a CO, but is there going to be a subscript on it? Yes, it's a 2, and there's going to be an S, and the S will have a subscript of 3. And then you just make sure that they're not a common denominator, and there's not 2. So now we're going to do calcium sulfate. And this really actually is the examples of the kind of stuff that you're doing that the assignment is due on Monday. So we have calcium sulfate. Calcium is a Ca. Okay, and you'd have to either look up or know the charge. The charge one's going to be a 2+. It's in the second column, but it's also going to be listed. It's a 2+. Sulfate is one of the, I guess, more difficult ones because it's a polyatomic anion. And it's SO4, and it is 2-. Jen, can I make them remember the common polyatomic? I'm not going to have you guys. You may, by the end of the semester, after writing it up so many times, you know them, but I'm not going to ask you to remember for this test. Okay? So now we just write the formula, Ca and SO4. Now the question is, are there going to be subscripts with the calcium or the sulfate? If I don't skip any steps, what I would do is you would put Ca2. The sulfate all behaves as 1, so you put parentheses around it, and it would be a 2. Because see, these are 2 and 2. But since they're both divisible by 2, the 2's cancel. And so that's with me not skipping any steps. So it becomes calcium sulfate. Oh, whoops, there we go. All right. So those are ionic ones. A lot of times when we're talking about a covalent, whoa, that's supposed to be an O, a covalent compound, the terms that they many times will also like to use are called molecular compounds versus an ionic compound. These are, remember, almost always between nonmetals. So things like carbon monoxide, carbon dioxide. And I even think that these are easier to name than the ionic ones. You always put which one's more metallic-like first. That's why it's carbon monoxide. Carbon comes before oxygen. Oxygen's more non-metal. So let's just do some examples. 2. And so this very first one in O2, what would its name be as a covalent compound? Which one comes first? Which one is less non-metallic? Or you can think of it as more metallic, nitrogen. And so what's its name going to be? Just nitrogen. You just write it out. It's nitrogen. And then we have oxygen, which the oxygen becomes oxide. Now, the one thing is with the covalent ones is we have to indicate the number, okay? Whenever the first one only has 1, you do not say mono. We don't say mononitrogen, such and such. And once again, I just always think of CO2. CO and CO2. It's carbon monoxide and carbon dioxide. We don't say monocarbon monoxide and monocarbon dioxide. We say carbon. Okay. But what prefix do we have to put in this one? It's for the 2, and so 2 is di. Those are technically 2 separate words. So it's nitrogen dioxide. Now the P is phosphorus. And so which is more metallic-like, oxygen or phosphorus? It's phosphorus, okay? So it comes first. So we know there's going to be a phosphorus. I'm deliberately leaving spaces before each of these, just in case. And we know oxygen becomes oxide. Just like if it's sulfur, it's sulfide. Fluorine and chlorine all become fluoride, chloride, bromide. Selenium becomes selenide. But if I actually write it down, you put selenium, I can't say seleniumide. I would use it because you got the idea. But it's called selenide. Phosphorus becomes phosphide. Carbon becomes carbide. All right. Now the question is, we have to account for the subscripts, the 2 and the 10. And so since this one isn't just 1, we do need to put the correct prefix in there. And so what's the prefix for 2 again? Di. So this becomes diphosphorus. What about 10? This is one, I mean, you do just have to memorize your numerical. It's DECA, D-E-C-A. Okay. Now it is true, like mono means 1, but they dropped that one O to make monoxide since oxygen starts with an O. But if you wrote monooxide, people would understand. But yeah, this is diphosphorus, decoxide. The other, another one that's common is PO5, which would be phosphorus pentoxide or pentaoxide. There are times I've seen decoxide where they drop that in A and that's the only other thing. Oh, and an acid. They talk about acids. And all acids mean, at least at this point in time for this class, first of all, it's got to be an aqueous. We're talking about an aqueous solution. And it means that it dissolves, or when it dissolves in water, it gives off an H+, which is a hydrogen cation. Yeah, I'll put a little, which is sometimes also called a proton. So if we go all the way back to the beginning of this chapter or the chapter right before it, hydrogen has 1 electron and 1 proton. So whenever it loses its 1 electron, all that's left behind is a proton. And that's why it's H+. And that's where pH comes from, which is important medically. If you go to more advanced chemistry, I don't think some intro to chemistry goes into it. There are a couple of nuances, like there are a couple other definitions of acids, but this one's called this one's called the Arrhenius. It's also called Bronsted-Lowry definition. I don't think the book goes into the details of that is. And so I mean that's about the extent of what. Once again, I would give you table, except for HCl and HBr, because whenever they're a gas versus a liquid. Okay, the other big, and to me, I'm really surprised. This next topic that we're going to talk about is really important later on. Yet for this chapter, they just kind of threw it in, like almost like the last thing, and literally it's the last thing that they threw in. And it's called formula mass. It's actually very simple. But it's so important for the rest of the semester. Sometimes people also call it molecular weight, depending upon if it's an ion versus a covalent compound. So a lot of times since I'm a biochemist, I use it interchangeably. Traditional chemists, especially inorganic ones, would get really upset and say, no, they're from, but in nursing and medicine stuff, we usually say formula mass and molecular weight interchangeably. It's literally how much based off of a chemical formula, how much what's the mass of that compound? That's it. And so, but it's very important for later on. So let's just do some examples. You have to have a periodic table for this, or I'd have to specifically tell you what it is. Tell you each of the different elements, what their mass is. Do not memorize, unless you have a photographic memory, please do not sit there and memorize the atomic mass for all of the elements. That would be, there may be some that you kind of pick up on from just using them so often, but. So let's do some examples. We're going to do H2O. We can do sodium chloride. I'll change colors. And then let's do one that's more complicated. Cobalt 3 sulfate. Okay, so that's one. That one is probably as hard as it's going to get. You're close to it. Because of just the fact that there are so many. Okay. So let's start with water. To figure out the formula mass, sometimes, another term that they like to use, sometimes formula weight. We literally just, you figure out how much the hydrogens weigh, what the mass is of the hydrogens, there's two of them, and the mass of the oxygen. And so that's given right off the periodic table, that's the atomic mass. So for this one, I've seen people write it out two different ways. You can write out long ways, especially for the ones like the cobalt sulfate. I like to write it out vertically, like this. Just because that's the way that, my mind works. And so for the hydrogens, there's two of them, and each one, if you look at the periodic table, it's roughly 1.01. Some periodic tables have more decimal points, some of them will have less. But each one weighs approximately 1.01. The oxygen, there's only one of them, and it's 16. I haven't memorized, I think that one says, 15.99994 or something. And so if you do it this way, you're probably less likely to make mistakes. So this becomes 2.02, that's 16. So it becomes 18.02. And it's atomic mass units right now with the atomic column. So that's it. But it's fairly simple. We'll find out the cobalt 3 sulfate is one of the more, just because there's so many different elements involved. So for sodium chloride, we have an Na, and there's only one of them. There's only one Cl, so we're just going to literally add these two together. I don't have these memorized. 22.99 for the sodium. Chloride is 35.45, I think. Yep, 35.45. And we would just add them together. So I don't have my calculator out, so double check my math. 10, 14, 7, 8. So it'd be 58.44. And once again, for this exam, and throughout the semester, I'm not going to take off based off of significant figures. Just because, because of the time constraints for the class for the semester. You just want to be careful if you do too much rounding, because I usually don't round until towards the very end. Just because if you round and something has lots and lots of steps, then your final answer will be so far off from what the real answer is that it can be a problem. So I'm going to give you a moment to at least start to set this one up. And I'll give me a moment to get my calculator out. Come on. I'm not taking a picture of you. Okay. I'm just going to raise all of this up. So I have plenty of room. This is the hard part about cobalt 3 sulfate. Remember, you have to do everything in the parentheses. So there are a couple of different ways to do that. Like I said, I like to write it out. Each one, we know we're going to have CO, we're going to have sulfurs, and we're going to have oxygens. That's not a zero, that's an oxygen. It's just trying to figure out how many of each thing, how many cobalts do we have in a cobalt 3 sulfate? There are 2. See, 2. No. So, we're going to have 2 times cobalt. I don't know how that one memorized. 58.93. Sulfur, how many total sulfurs do we have for every cobalt 3 sulfate? 3, because there's 1 in the parentheses, and there's that 3 outside the parentheses. So that's why I say it's the hardest. There's a 1, it's implied, but 1 times 3 would be 3. So there's a total of 3. It's 32.07? No. 066. Well, I'm going to round it up just a little bit. All right, and now how many total oxygens are there? 12. Because that's why I said this was where it gets. There's 4, but you have to multiply it by that number outside the parentheses. And so that's why there are 12, a total of 12. Oh. Okay, thank you. So there's 12, and it's 16.0. And I'm just going to go ahead and keep on writing it out that way. So wait. Come on. Phone, wake up. Clear. Times 58.93. 6. 3 times 32.07. And I do suggest on something like this, I would write out I'd write out your work. That way, just in case you transpose, I've seen people transpose numbers or something. That way you can get at least partial credit for it if you write out your work. And you got it wrong. 117.86 plus 96.21 plus 192 equals. So this one is 406.07 AMU. That's it. That's the end of this chapter, really. And so it's not. There's not a. It may seem like